Cool, so today I'm going to deep dive into ECS. So I'm a senior DevOps engineer working for the Sale for New Zealand team. And what we do is have a software product called Carnival.io, which is built around mobile marketing. So push messages to your phone applications and then doing analytics and engagement metrics around those phone apps. I've been doing stuff for Amazon for about 6 years now, and our current environment is 100% Amazon related. And the reason I'm talking about ECS today is that we went for a big project last year to migrate a whole bunch of our workloads onto the ECS platform. So I'm going to take you through what ECS does, and then start looking at some of the deeper aspects of it, things it does that you might not expect, or things it does that are not necessarily great. We can talk about all the benefits and the negatives of it. So I just want to really quickly touch a few fundamentals, just so we're not leaving people behind. So if you're not familiar with what a container is, it's essentially a way of componentizing an application or dependencies and a Linux operating system into a nice deployable package or container. And the host operating system runs these in a self-contained, in a isolated fashion. So no one container can mess with another container, provided that the platform actually works as expected. And this is a really, really popular design model. Most people who have dealt with a younger company recently will certainly be using containerized environments, and even your traditional enterprise, people are talking about containers and getting excited about this. So if you haven't already played with them, definitely check out the links on Docker, learn a lot more about them. I'm going to mention Docker a lot. Docker is a technology platform for running containers, and that includes functionality for packaging and distributing containers themselves, so like the binary artifact of what you've built. And we often use Docker to refer to the Docker image file, which is the actual binary artifact that we're going to send around. So what is container orchestration? Why do I care? What does all this mean? So a simple Docker environment that you may have come across would involve having a laptop, like your developer's workstation, running Docker, and then running various containers on top of it. So I may have a container running Apache on top of a CentOS base, or a PHP application on top of a Ubuntu base. And this model works great. You just load on different containers, and it's all beautiful. And of course, at some point, you decide you'd actually like to take this to production, and a very typical design pattern, a very typical pattern for a newbie to container world will be to spin up an EC2 instance, and then install Linux, and then have Docker on it, and just load on their containers. Pretty much just mirroring what the laptop does. And it is actually a valid model for a small organization, because you can make it highly available by copying those EC2 instances with their associated containers to make sure that if any one fails, you don't lose your functionality. And there is actually a design model in Amazon for this with Elastic Beanstalk called the multi-container Docker platform. And if you're not familiar with Elastic Beanstalk, it's generally used to say, hey, I've got an application code base, please deploy it to Amazon EC2 and make it redundant and handle deployments. But you can also tell Beanstalk to say, actually, I've got a bunch of Docker images, can you please deploy those and make them redundant and handle the deployments? And it's a totally fine model, and it's quite useful if you're, say, a small organization with one application product, and you just need to run a few different containers to support the app. It's totally feasible. But at some point, you're going to have a problem, because if your organization becomes bigger and bigger, you're going to have too many containers to fit onto that single server type environment. And there will be a problem. It might not necessarily be max CPU, but you might run out of your I/O, or you saturate the load balancers, or some other limitation. And even Amazon has a limit. Once you get to 4 terabytes of RAM, you're going to have a problem. So we have to have a solution for that. So the other big problem you're going to have at some point as well is you're going to end up with a wide-ranging number of containers where you can't simply dump them all on one machine. You may have one microservice that needs 2 containers, and you may have a giant, big, monolithic application that needs 50 copies of itself and 4 terabytes of RAM. So you can't just keep squeezing it onto one box. And this is where container orchestration comes in. And really, really on a really, really simple level, you pretty much pour a whole bunch of EC2 resources in, a whole bunch of containers in, and your orchestration technology is supposed to figure it all out and make it work, which is always, the fun is in the details. So what's the responsibility of the orchestration system? So it's responsible for figuring out where the containers should be placed out of all the compute that you've provisioned. And so it takes into consideration how much resource, so CPU, I/O, memory that your container needs, and figures out where it can fit them on your environment. And it's responsible for handling typically your deployments, as well as your HA and rollback and redundancy of your containers. So if a particular container crashes, your container orchestration system should go, oh, I've lost my WordPress container, I'll relaunch it over here. Or if a particular container says, hey, I need 2 gig of RAM, and I'm on a box of 1 gig, it's going to go, well, this is not going to work, I'll move it to an appropriate place where it can operate. And your popular orchestration tools generally integrate with the major cloud providers. So in the case of Amazon, you want your containers to be able to talk to your load balancers. So when a container starts up, it connects to your load balancer and can receive requests. You might want to be able to attach storage, you want IAM roles, those kinds of things. So there's a bunch of options in the market. This is just 3 of I'd say, probably the more major players that we're seeing. So ECS, Kubernetes, you often see it abbreviated as K8, and Mesos, which I think is from Apache. So we've got options. Why do we care about ECS? So the situation for our team back in late 2016, early 2017, is that we had an existing containerized environment. So the team had done a really, really good design choice that they'd already packaged all of the applications and microservices into containers, but we were using a core OS environment with Fleet as the orchestration tool. And Fleet was a really, really cool tool for its time, but it kind of got deadlined and then didn't get any innovation done for several years because the teams went on to work with other technologies like Kubernetes. So we had a situation where we had to get off Fleet because it just wouldn't meet our requirements. Probably the biggest barrier is that Fleet couldn't do auto-scaling. And as our team and our product was growing, it was really, really critical that we could respond quickly to growth changes. And to give some context as well, the team that we had good Amazon understanding, really, really good development team, but we had limited DevOps resource, aka myself, and I wanted to make sure whatever solution we chose didn't require excessive amounts of infrastructure skill set to operate, because we just didn't have that level of capacity in the team. So we looked strongly into Kubernetes. I mean, Kubernetes is a fantastic platform right now, but back in 2016 it wasn't quite as mature as we would have liked. There's still quite a lot of messing around in its code base to debug problems or to understand how to perform certain configurations. And that's certainly changed a lot in the past couple of years. The other big upside for us at the time with ECS is that it was fully covered by our Amazon support contract. So Amazon provides support for that's really annoying. Why did it do that? Amazon provides support for the entire platform. So the EC2 instances, the AMI image, the Linux operating system that we're using, which is Amazon Linux, the Docker version combinations, the kernel version combinations that we're using. So it's really nice having one vendor to strangle or thank when you have a particular problem and need their assistance. The other upside of ECS is being an Amazon product, as you can probably imagine, it included, that's going to get very annoying. Stay on that screen. I think what's happening is it's actually dropping offline, and then the other tab is like, hey, I'm offline. It's like, well, I know you're offline, mate. I don't need you to tell me about it right now. I'll just put it on my phone so it doesn't keep doing it. Where are we? Yeah, it's not just vanity, it's actually recording. All right, let's see if that works. Might be a more reliable connection. So yeah, as I was saying, it's Amazon product. It features all the Goodbye. Can't still focus if you're not running. Please stay. Okay. So as I was saying, Amazon product integrates nicely with all the Amazon features we needed, like load balancers. So that's a nice upside for us as well. And the other thing that was kind of I guess you thought sealed the deal for us is this is late 2016. Amazon had just released a huge number of new innovations and features in ECS that made it really attractive to us. So I would say right now, if you've looked at ECS in the past, like several years ago, it's a very different product to what you looked at back then. They tend to do a huge dump of features around September each year. So yeah, every year it's happening, there's more and more stuff going into it, and it's changed quite significantly. Speaking of changing, the landscape's also continually evolving. So Amazon's announced recently again bringing out a managed Kubernetes service called EKS. So yeah, we're going to have the option of 2 different orchestration technologies, and we're not really sure yet what's going to happen on the outcome of this. For example, is ECS going to be a simpler system for my first orchestration tool, or are they going to compete with each other actively? Not totally sure yet. So it's going to be interesting to see what happens in the space and how they evolve. But Amazon supposedly is committed to maintaining both product lines for the future, so I'm interested to see what happens from there. So, okay, Kubernetes, we're not here. ECS, how does it work? So it uses a stock standard Docker system. So there's no modifications to the container format or the container platform. It's just Docker underneath, to the level that you can spin up your own Linux image of your favorite distribution with your favorite Docker version, and you can drop on the ECS agent, and it's a functional ECS node. Ultimately, all the intelligence is in the Amazon cloud. The ECS agent is just a worker to launch and terminate and do things with containers. The good thing is Amazon provides a Amazon AMI image with blessed versions of Linux kernel, the Docker version, combined with the agent version. So if you don't particularly like debugging the intricate details of buggy Docker versions or buggy kernel versions, you just go with the off-the-shelf image and have a nice relaxing time. So ECS will hook into ECR, which is Amazon's Docker registry service, but it can also support other independent Docker registries like Docker Hub directly, for example. So the cool thing about that is if you're a company that cares about the security and privacy of your application images, you can upload them straight into ECR and know that they're not going to be publicly exposed or on a third-party provider that you already haven't got an agreement with. ECS, of course, manages more than one machine. So in our case, we have it deployed. So it's deployed on a region, your cluster's on a region level, but you're managing machines across multiple availability zones. So in the case for us, we operate across 3 availability zones. We can lose any one AZ and still have sufficient capacity to deliver services to our customers. And ECS will just handle it automatically. You just say, hey, I've got service here, here, here. ECS goes, cool, they're on my cluster, good to go. So ECS, one of the little challenges was getting around some of the terminologies. So with ECS, they talk about tasks a lot. And a task could be one container, but it could also be multiple containers wrapped up into a single unit. So the best example for this would be when you've got applications that need another support application. So we run a large number of applications that use Mongo, and Mongo needs a Mongo router to know where to send its requests. So we'll deploy the Ruby application and the Mongo application together as 2 different containers in the one task. And that means you don't end up with only one running, you always end up with a paired deployment. Another case might be if you've got like a custom logging tool. So your application might be a container, your logging tool might be another container. They talk to each other and they're deployed as a discrete bundle each time. You can do CPU and memory reservations at a container or a task level. So task levels are a relatively new feature, so you can just say, look, this whole thing just needs 2 gig of RAM, you figure it out. But you can also break it down to individual containers if you really want to. And there's a feature or the concept of reservations. And with reservations, you can say, I want this container to always have at least, say, 1 gig of RAM available on the server for it. And ECS will make sure that based on all the reservations that you set in all the applications, there's always going to be at least that 1 gig of RAM. But you can also do a thing where you can go beyond the reservation with hard and soft limits. So you can say, look, I'm pretty sure this app just wants 1 gig of RAM, but if it really, really needs more than 1 gig, and it's available on the host, let it go over to maybe 2 gig. So you've got a few choices like that. And when it hits the limit, ECS says, look, you've been naughty, you're getting terminated. So it can deal with your leaking applications and so forth. But the reservation model is really important because once you start deploying this to a large fleet, you want to figure out how much CPU and memory you're actually using. So you want to set each task to have a reasonably accurate reservation for what it needs to operate, so you can figure out your resourcing requirements appropriately. You don't want to operate 100 containers on one server and then figure out that all those containers actually need far more CPU and memory than you've really allocated. Particularly important with like web apps, because a lot of web apps might be sitting around 200 meg, like a nice little lightweight Ruby app, and then the user uploads 700 meg file, and then all of a sudden you're using 800 or 900 meg of data. You've got to make sure you think about some of those considerations. So as I mentioned, ECS can place the tasks on the cluster based on your resource requirements, and you can look at the overall cluster and see how much CPU is being utilized, how much memory is being utilized, and break it down to individual machines and say, okay, what's going on in particular boxes. Right. The other key thing with ECS is a concept called a service. So a service manages the deployment of tasks and the registration into load balancers. So a task is a bunch of containers, but you're going to go, well, I tend to want more than 1 copy of my web app. So you say, hey, I'll create a service, and I'll say I want 5 copies of this task, and the service is responsible for making sure that it is always 5 copies. So the service will tell you, ECS, please launch this, we've lost one, or hey, we haven't got enough, boot some up, make them available. The cool thing about services is they've got built-in integration with ALBs, so you don't have to worry about trying to register your launch container with a load balancer. The service will just launch it, do all the registration for you, and when it shuts them down, it will do the deregistration from the load balancer as well, which is a big help if you've ever done that stuff manually. It's much nicer having it automated. So I want to talk a little bit about security and networking aspects of ECS. So one of the really cool things is that being a native Amazon product, you kind of expect some good integrations, and it doesn't fail to deliver here because it gives us unique IAM roles per task. If you're not familiar with IAM role, you might have used it before in EC2 instances. Essentially, you can say, hey, Amazon, this server, give it this defined IAM policy. And I don't want it to specify username and passwords, just delegate it when it starts up. And it gives it a unique credential set every time. So the cool thing about this role model is if your machine is compromised, you shoot the machine and the credentials are revoked. The next machine launches, gets allocated new unique credentials. The same model applies to ECS tasks. So if you're running a server with multiple containers and you've got, say, WordPress container and the batch data processing container, the WordPress container can't go talk to the S3 bucket full of all your customer data. They can only talk to the services you've allocated it. It can be isolated at that level, which is a nice feeling. There's a slight caveat here. You have to be careful with the host, because on Amazon, the host has its own IAM role, and the container can have its own IAM role. But if you don't put a particular iptables role in, the container can actually break out and use the host role, which, if you're following the Amazon standard guide, isn't actually a big issue because the host role is very limited. But if you've been a little bit creative and you've put maybe a few things you shouldn't have in your host role, this could potentially burn you in some funny ways. The other thing by blocking this is that also the containers can't do extra information exfiltration from your network. The container can't tell what its instance ID is or where it's running or any of that sort of stuff. You basically kept it blind and in the dark. This is actually referenced on the ECS IAM guide if you ever choose to look it up. I would actually recommend if you do an ECS deployment, just read the docs from start to end. It looks really big, but it's actually not as big as it seems. And it just gives you a really good understanding of some of the, I guess, oddities that you need to be aware of, like with any system. So networking. Well, the cool thing is ECS actually has a whole bunch of different options for your networking. So none does what you might think. There's also a couple of options. So host, I've not ever needed to use host. I wouldn't recommend using it, but essentially with a host model, your container is given a port directly on the host's IP address itself. So there's no other virtual networking going on. I don't know why you'd actually want that unless you're doing something really funky like SIP, where the IP address is suddenly important. Most deployments are going to want to do bridge, which is the default mode. And with a bridge mode, every EC2 server is allocated a private RFC 1918 network on the machine, and the containers all signed IPs within that range. To gain access beyond the host, you have NAT outbound on the host instance, and you have port forwarding on the inbound for incoming requests. Now, recently this got improved with a new feature called AWS VPC mode, and the cool thing about this is you can now attach a unique interface to every container, which doesn't seem that interesting, except it means you can have a security group per container. So with the default mode, if you have, say, an unsecured network database like Elasticsearch or Mongo, which don't require authentication by default, all the containers on a particular host would have access to that database. So that means, like our WordPress container and our data processing container can both talk to your Elasticsearch system without logon, which is obviously bad. So with the default mode, it's really important to secure them. But with Amazon VPC mode, you could say, hey, the WordPress container security group doesn't allow it to talk to Mongo or Elasticsearch. It's completely isolated at a network level and an IAM level, which is a really, really cool feature. And we'll come back to that. So default mode, cool thing about it, handles almost unlimited number of containers on your machine. So if you're getting a really, really big instance, you can just go nuts, launch whatever you need. And it's been really reliable. So we do a significant amount of traffic for our systems. We've had no issues to date with the networking layer, which is fantastic. Couple caveats. So all inbound requests need to transit via a load balancer. And I will say there's a slight asterisk there. There are ways of doing inbound requests on the default mode without a load balancer, but they're a bit gnarly, and I don't recommend it because then you're rolling your own integrations, which is a story for another day. Ultimately, your model you should assume is any service must be on a load balancer, whether it's TCP or HTTP. Either way, you're going to need the load balancer. And as I mentioned before, it shares a single security group for the whole ECS cluster, which means any network resources you talk to have to have authentication, otherwise your least secure container now has access to that network resource, which is generally not going to be fun. So I mean, I would always recommend, even with security groups, you should still roll authentication on your databases, but some products, Elasticsearch, make it a little bit harder than I would actually like. Thanks, guys. So as I mentioned, dynamic ports. So the cool thing about this is if you're deploying, say, 50 apps that all sit on port 80, you don't have to go, oh no, I've got a number 81, 82, or 80, 80, 81. You don't have any of that hassle. You just say, you know what, they're all running on port 80, ECS is your problem. You're the orchestration tool, you fucking figure it out. And it will do that. So in this case here, we've got a service this is a load balancer, the big one's a load balancer. And a service is operational and the system's registered all the hosts to the load balancer with a range of ports. And those ports map through to dynamic ports that's assigned on the host. And then the only little trick is on the EC2 instance security group, we have to allow access from the port range, which is down below, from that particular load balancer security group. Which seems a little bit scary because you're like, oh fuck, there's so many ports that have been opened. But the good thing is it's actually not that risky because what you've said is Amazon load balancers, which are a trusted thing, have access to these dynamic port ranges. And then the load balancer itself has a security group on it, which allows you to tightly define who can even talk to the load balancer in the first case. So from a networking security model, it's actually pretty good. But I mentioned before, Amazon VPC mode's around, and it's really, really cool because I can have a security group per task. I really, really want to use that. The other upside of that is also they would let me use direct communication between my containers on the network. Because with default mode, if I've got a container on one EC2 host and a container on another EC2 host, they can't easily talk directly to each other. They have to go out for a load balancer. Works fine for our environment where everything is basically an HTTP service, which we want load balancers on anyway, but it doesn't necessarily suit everyone's operating mode. The problem with AWS VPC mode is it's subject to EC2 ENI limitations, which is essentially the max number of network interfaces that can be attached to a server. And that just sounds like a weird side note, who really cares, what does it actually mean? The problem is it's actually a really significant limit. So EC2 has the ability, or has a limitation on the number of virtual network interfaces for each machine type, and that changes as you go through the different class of machines. So we're talking about a situation where you might deploy one of the largest C5 series, and you've got a whopping amount of memory and CPU. You're like, great, I can run hundreds of containers on this thing. But if you're using Amazon AWS VPC mode, you can run 14 containers, which is not necessarily what I want to do if I don't want every container to have, say, 10 gig of RAM. Now, it might work fine if my environment was, a large bunch of memory-heavy database containers that I wanted to allocate huge amounts of resources to, but it works really badly for, I want to run an absolute huge pile of Ruby applications, which need 512 mega each. So yeah, it's a really annoying limit, and I hope that Amazon is going to evolve this and change this at some point in future. But it's a really, really nasty caveat that sort of prevents me from really endorsing the AWS VPC mode, which is a shame because everything else about it is fantastic. That's kind of how I feel about it. I'm getting all excited about EKS now and Kubernetes because Kubernetes has a really, really sophisticated networking model. But it's a shame because AWS VPC mode is still a very lovely person.
You say, for that C5 instance you put up, you can only have two containers on.
With the AWS VPC mode, yeah. So you could mix it. You could have a bunch of containers running default mode and then two running on AWS VPC mode. But then it's a bit weird because you'd have like certain containers that have more features than others, which you don't really want in your environment. Yeah, I think it's a really silly limit. It's a bit of a shame. Cool, CI/CD. So, cool thing is Amazon has a whole bunch of examples of how to do your CI/CD pipeline with ECS. The first two I don't particularly recommend. They're older examples. They recently made it a lot easier by bringing out a feature for AWS CodePipeline called Amazon ECS targets. So in the old days, you'd have to do some sort of deployment pipeline or build system like Jenkins or even CodePipeline, and then you'd have some nasty bit of scripting work in between, and then you hit an ECS deployment. Whereas now you can just grab CodePipeline, ECS natively on Amazon console, stick them together, and you've got a deployment pipeline, which is fantastic. So if you are going to do a clean deployment, I would check out that particular design as an option. I will send out the links on the meetup page after this, so you don't have to try and take notes. I'll talk a little bit about our pipeline. So we built ours before this feature was available. I actually really like it. I think we're going to stick with it. So our whole model is to actually store the configuration outside of ECS. Because one of the annoyances of ECS is that your configuration lives on the task definition, which seems logical, the task is the app, the config should be there. It's a little bit annoying though when you want to put the same config on multiple applications. So a typical one will be the address of your database server or a particular API endpoint. With the stock standard ECS implementation, you have to go for each one and update each one. I mean, yes, you can automate that, but it's just a little bit annoying. And particularly in our environment, it's actually really, really common that so much of our config applies to multiple systems. So we developed an approach where we store all of our configuration in etcd. And with etcd, we've got a hierarchical structure. So when we deploy an application, we can look up and say, oh, I'm web service, and web service inherits common, which includes things like the Elasticsearch server endpoint, which makes life a lot easier for us to deploy. And the approach we took is we had an existing build system, which works nicely, takes the code base after a change is made, compiles a Docker image, shoves it into ECR. And we ended up just hooking into ECR using Amazon CloudTrail events. So CloudTrail, if you're not familiar, can actually expose any API action that took place on Amazon. So in this case, we're like, hey, CloudTrail, just tell us when someone did a ECR put request. And it's like, oh, someone just dropped in a WordPress image. And we're like, cool. So we trigger a Lambda, and that Lambda grabs the configuration from etcd, applies a configuration to the task definition, sets the task definition to that particular version of the container that just got uploaded, and then deploys it to our cluster. And once we hand it to ECS, what basically we're saying with ECS is, here's a new task definition. And ECS goes, well, okay, you want me to roll out version 10, and I've got version 9 running, and it handles the whole strategy of rolling out the upgrade based on the config you've given it. And I'm not going to go too much detail about that, but the one cool aspect about it is you can say, in your ECS service, set the minimum and maximum number of containers that you want to allow. So when you do a rollout, if you said, I want a minimum of 80% of machines, it will stop 20% of your fleet, upgrade 20% of the containers, and then start them back up. And it will do a rolling upgrade of your whole cluster, which is actually really, really cool. So our environment is actually slightly more complex than that because we start doing crazy stuff with CloudFormation. So when we launch a stack, we actually we've got a template for containers of task definitions and services, and we download the configuration from etcd using CFN custom resources, which is really, really fun. I do recommend playing with custom resources sometime if you haven't already, but it makes things a little more complex. So don't get too scared. If you're starting from ECS from scratch, just grab the code deploy pipeline and go with that, at least initially, and it'll meet most of your requirements. One of the key things we did is we really wanted to see when stuff's happening on our cluster. And we've got a model where our DevOps team, me and one other gentleman, and our development team are basically embedded. And so we don't want it to be, oh, well, hey, Mr. DevOps person, what's happening? We want everyone in the team to feel empowered to release stuff and understand what's happening on the system in production. So every change that we make to the clusters feed into Slack. So we can see, oh, someone's updated the production web API from one version to another version. But we also designed it so it would tell us when configs changed. So we can see, hey, someone's added a new environmental for the Kafka server or StatsD server or things like that. So we know who's messing with things in production. Yes, it's in the change control process, but there's nothing quite like knowing, oh, this thing changed, and then 5 minutes later seeing alarms go off. It's much more mentally pleasing when you're debugging. And this actually worked really, really quite well for us. A little bit of logging. So cool thing about ECS, and to be honest with most orchestration systems, is they can solve a lot of the centralized logging problems for you. So with ECS, when you build your task definition, you can say, hey, I want to use syslog endpoint as for all my logs for my application, or I want to use, in our case, CloudWatch logs as the endpoint for our logging information. And the model we took is from the 12-factor playbook, and we just said, look, we want every log to just go to standard out, standard error. We don't want to mess around with files on disk or any of that stuff. Just spew it out, and let the orchestration tool pick it up and handle it. And that works really, really nicely. ECS handles like the log buffering problems and just figures out how to feed all your stuff through, which is really, really cool. We actually developed a tool on top of this called the ECS Parrot. So one of the annoyances is if your container's just crashed, you're like, oh, I've got to find my logs. So we'd have to go to console, go to CloudWatch logs, and find which service it was, and click on that. It was just, it was like 5 clicks. That's 5 too many. So we developed ECS Parrot, which sends a log message to Slack saying, hey, this task just died. It ran for a minute. There's probably something wrong there. It should have run for, maybe a few days. And it gives us a link to the container logs. So we can just click on the log link, and it takes us straight into the Amazon console to that exact instance's logs, so you can see why it died and what happened from there. That's actually open source if you're interested. So I'll send the links out to that later on. We have actually started moving away from this a little bit in that we still send all our log data to CloudWatch logs, but if you ever use CloudWatch logs, the interface is kind of like taking a brick to the head. It's not that pleasant. So we've started sending all of our log data into Kibana. So it's available in CloudWatch logs, but also in Kibana, so we can analyze it there and read it in a more pleasant format. Right, autoscaling. This is the whole reason why you want containers anyway, right? So I hoped that the workload was ideal for autoscaling because we had a very time of day type pattern, including quite significant variation between our min and max load. And you can see it before we started autoscaling in the ECS metrics. So this is the overall cluster utilization graph, and you can see at some point we're using 8% of our compute. So we're throwing away a huge amount of money, but then when it gets busy, we're using 40%, and we still have to have additional capacity to handle rare bursts of traffic. It's not a very cost-efficient way of operating your platform. So there's two parts to make it work with ECS. The first is you actually need to scale your container workload itself, and then you scale the underlying compute to meet the amount of resource that container workload requires. So this is all configured via ECS services. You tell the service, I want to scale between this size and this size based on these triggers, and it will increase and decrease the system. So it looks a little bit like this. And this is all stock standard Amazon. There's no custom programming required for this. We're basically saying, hey, for the ECS service for my website, when the CPU metric is maybe 70% utilized, I want you to trigger a launch of additional tasks. If the CPU is at 50%, I want you to go kill some tasks. So the autoscaling logic within ECS is increasing and decreasing the number of tasks in a given service, which is why that whole service model is so important. The task is just doing a thing. It's up to the service to figure out how many of the tasks there should be and whether they should be launched or terminated. If you're doing web applications, your sort of initial thought is, CPU is important, I'll monitor the CPU and scale on that. The caveat is web apps start performing a lot worse before they get even close to the maxed amount of CPU. Because when your CPU is busy, say it's at 90% utilization, what's actually happening is some requests are getting blocked, waiting for resources being completed. So your latency starts going up and up and up as you get higher and higher with your CPU utilization. So we've ended up targeting about 70% of our max for applications, for web apps, because any more than that, the latency starts going from like 3 milliseconds to 30 milliseconds, and it's not end of the world, but we're still here. We've also started feeding in other metrics, so you can feed in any CloudWatch metric you want to use as part of autoscaling logic. So we're feeding in things like the latency on ALBs. Like, if the CPU is low, but the app's still performing like crap, just launch more of it and see if that helps while we debug, which is actually quite useful because if you've got something like a database bottleneck, at least you're opening more boxes so they can queue more connections and hold them in memory and stuff like that. We also use things like we started logging all of our queue-based architecture. We started logging all of our queue metrics into CloudWatch so we can trigger scaling based on queue depth. So if you've got a batch processor and the queue's getting really big, we're like, we'll launch some more batch processors, and it works that way. The other key part is you need to scale the underlying compute. So we've got a container workload that grows and shrinks based on what it needs. Well, now we might as well just turn off everything that's beyond the total size of that. And the good thing is most of it is stock standard Amazon stuff. So the auto-scaling policy on an EC2 group, launching and destroying machines. And we use what's called a scaling targeted policy. So we say, hey, look at the CPU reservation metric for the ECS cluster that we care about, and launch and destroy EC2 instances based on what the reservation size is. So when we launch more tasks, they start reserving more CPU, more memory, that reservation goes up, hits say 80%, we go, we're starting to get it full, we start launching more EC2 servers via the auto-scaling group. When that reservation drops down to say 50%, we start shutting down servers because we're now wasting money. Now that part's all native Amazon, there's nothing unique there, and if you've done auto-scaling before, it's literally the exact same thing you've always done with auto-scaling, except that you're launching an ECS AMI rather than something else. The annoying part is when it comes to termination, because auto-scaling is a very helpful system, and it goes, you don't need the server anymore, I just turned it off. And you're like, yeah, but I was running some containers on it, and they were in the load balancer, and they were receiving requests. Turns out the autoscaler doesn't care, doesn't like your containers. So one of the annoyances is you actually have to integrate the autoscaling group with Lambda to perform a draining operation on the EC2 instance. So what happens is autoscaling group says, right, I'm going to terminate a box. but we've put a hook in place that goes and talks to our Lambda, says, hey, this machine needs to die. We trigger an event on the Amazon API to drain it, which means ECS is told this machine's going away, find new homes for everything on it, and ECS stops that container or stops the task and relocates the task to another machine. And then once that relocation is complete, that machine's now empty, and we can send a termination request and let it be shut down, which takes about 3 or 4 minutes, which is fine because they're shutting down machines. It's not delaying our launch time or anything like that. It's just machines shutting down in the background. But it's really annoying that it's not natively built into ECS, given that ECS is an Amazon product and autoscaling is an Amazon product. And you're like, hey guys, maybe get your team in a room with a beer and figure something out. The one good thing I will point out is Amazon do provide a reference implementation for this. So you don't have to go, oh fuck, how do I make all this work? There's literally a Lambda that you can grab, drop it into your CloudFormation stacks, and you have the ability to now do autoscaling. So it's still pretty easy. It's just a bit odd when you'd think it'd be built in from day one. So when you put it together, you suddenly start seeing the interaction. So the key part there is on one side we've got our containers scaling, shrinking, and on the other side we've got our compute doing the same based on the reservation from those containers. So we're feeding the metric, like a cause and effect. The more containers we launch, the higher the utilization is going to get, the more servers need to launch, and vice versa. So that works really, really well for us. We've had this in production for quite a few months now. Like my next 5 says. So saving about 3 to 5k USD per month, which was not an insignificant amount on our bill. The other really cool thing about it is we've sort of had to stop thinking about, do we have enough servers for XYZ? You still want to care about you're not wasting resources and you're allocating the appropriate amount of memory and CPU to your project, but we're not like, do we have enough memory to launch this one new app? It's just like, just launch it. The system will figure it out and make sure it's available. And the other cool perk we've got is the EC2 hosts get rotated almost every 24 hours for us. So when we push a new AMI image, like a new version of Docker, we just say, hey, update the autoscaling group, and then it'll slowly roll it out over a 24-hour period so we can do like A/B comparison on how the instances are performing. So if you rolled out like a really dodgy kernel, you can be like, oh look, the machines are now 10% slower because we patched Meltdown. I guess you can't do much about that one. But yeah, it's quite a useful model for us. And that graph from Datadog just showing the number of servers in the cluster as the day goes on. So, quite significant cost savings. We did have one little issue though, in that, as I mentioned at the start, our product's about push message marketing. And a single customer could suddenly decide at 4 a.m. New Zealand time they want to send 3 or if not more messages to a whole bunch of cell phones. And the problem with the system is we can deliver messages really, really fast, but every time we deliver a message, that sends back some telemetry to our system. And if a user starts engaging with the app, that sends back a lot of telemetry to our system. And that creates a little bit of a load spike, as you can see on that graph. The ratio change is quite brutal. And autoscaling works beautifully, but autoscaling assumes that you've got a load pattern changing over, say, a 5 or 10, maybe ideally even 15-minute period. It doesn't handle, I was quiet and now I'm slammed. So we developed a thing called a push scaler, and you can tell the graphics department did not look at my slides. But ultimately what we're doing is we get a SNS message from the application that generates the outgoing push, sends it to a Lambda that we developed, saying, hey, you know what, I'm going to send 3 million push messages, and I'm going to do it at a rate of 1 million a minute. You figure out what you need to do to support that. And so it becomes a responsibility of our system to go and launch more containers and more EC2 instances. So if I put it on the diagram that we had before, it's that little bit at the bottom. And what we're actually doing is we're plugging into both sides. So when we send our large push, we immediately go and start launching API endpoint containers, or tasks to be more accurate. So we say to the ECS service, I need to go from 10 to 20. And at the same time, we also start launching more EC2 instances, because we know that if we just launch more tasks, by the time that filters down into, we need more CPU, it's too late. We've already hit the load spike, we've run out of CPU, things are failing, and there's 500s everywhere, and PagerDuty is melting down. Whereas by launching more compute and more containers at the same time, we're actually ready to go in about 90 seconds, which works really, really nicely.
And that calculator is done by your team's understanding of the ripple effect of sending out 300,000.
Yeah, so the development team were really helpful and basically said, look, we can provide you with what you want, what do you need? So I said, look, I just need to know how many devices are pushing to, at what rate. And then using a very scientific feeling of guessing, sort of roughly worked out how many servers you need for how many pushes.
You've got that data, right?
Yeah, we do.
You could look back.
Yeah. So it's not as amazing as going, oh, let's analyze the last 24 hours of sending speeds and figure out exactly how much compute we need. But we know, for 1 million pushes, you might need, say, 10 machines.
And I assume you're on the side of caution.
Yeah, exactly. If we throw a little bit too much money at it, it's fine. We don't cause an outage, and we're still saving an absolute fortune by not running that max compute continuously, which is kind of cool. And so let's see a graph of it working. These are Datadog graphs, but they're extracting data from CloudWatch metrics. So just a bit nicer to look at than CloudWatch. So on the top, we've got running task count. So we're chilling out, launching a whole bunch of tasks. We do the same thing with the servers because containers do need servers to run on. So the same thing happens there. And you can see below that the actual pushes were sent just slightly after the time that we launched additional compute. And we can see the incoming request on Nginx, getting slammed with a whole bunch of requests. And I don't have the graph on it here, but the real key, I guess, validation of this for us was looking at the Nginx latency graph. Because before what happened is during a busy period, the latency would be like, maybe 10 milliseconds, 120 milliseconds, and then back down. Whereas now it just stays flat. It's like, don't even care, because the resources available to support the volume of requests we've got. As a caveat, of course, it doesn't solve the fact that your database still has to be big enough to handle your peak load, but you can't have everything for free, I guess.
Did you also see that from an actual impact? Like, obviously you're saying it's being lowered. But did you actually see less engagement or more engagement?
Didn't measure the customer engagement side. The engagement for us was more, if we don't do this, people will raise support tickets, which is a certain type of engagement.
You can infer that it was a good change.
Yeah, definitely a good change. And it's actually saved us quite a few times because we had a bunch of larger customers come on board, and then, both of them obviously colluding, decided to send huge pushes at the exact same moment in time. 9 a.m. on a business US day is quite a popular time, it seems, to push messages. And, if you get 2 customers sending 6 million pushes each, you're like, oh, shit. The system's actually handled those and absorbed those spikes for us, which has been a real saving grace. If we had, a manual set of peak size, our peak probably wouldn't have been high enough, which is awesome. Wasn't without challenges. As I mentioned before, we've got like 90 seconds to launch. So we ended up doing a whole bunch of work with Packer and AMI baking. So although Amazon provides a really, really good AMI image, we actually take that image and make a few alterations, just some unique aspects of our environment. And we use Puppet and Packer to actually build that out. Puppet purely because we're a fully Puppet shop already and it's just easy, but it doesn't really need to be that way. The other real problem we have, and we're still having to some degree, is that our push platform gets better and better. It turns out, people keep innovating and improving stuff. And the EC2 launch time is starting to become a problem because our teams made the system so fast at generating pushes. The saving grace is that most customers can't handle the amount of load they generate either. So a lot of customers are like, can you please only do, maybe 100 a second? Our own web server's getting overloaded. But of course, you do have a few very technically savvy customers who can absorb that kind of load, who are asking for essentially unthrottled delivery speeds. And for those customers, 30 seconds is a noticeable lag, which is a slight challenge for us, which Amazon's kind of come up with a solution for called AWS Fargate. So this was announced late last year. And the whole idea behind that is we all care about running in containers, not servers. So why don't we just sell you containers as a service? Which is, pretty compelling advertising, really. So all the EC2 work I did is now irrelevant. And the really exciting thing about it is you can launch, like Amazon claim, you can launch tens of thousands of containers in seconds. So it basically sounds like container Lambda. Here's a Docker file, here's a Docker image, please run it this many times really, really quickly, and it will do that. The only caveat is pricing isn't suitable for continual operation. So I will happily pay the pricing that it charges for the burst workload. So that spike of requests, happily pay a big premium just to get the capacity and not worry about server launch times. But I can't recommend it to someone going, we don't have any infrastructure people, we just want to have the simplest possible container platform, we'll just run it in Fargate and not worry about servers, because the continual runtime is quite expensive by comparison to traditional compute. We're talking $46 rather than $8. So it's quite a premium for not having to do a little bit of lifting with a few EC2 autoscaling groups. But it's still a really exciting product. I'm really, really keen to play around with this, particularly for our burst load. Just put all the base stuff on compute and then use it when we just need an extra quick launch time. Is that all? No, of course not. There's a whole bunch of other great stuff. So there's a feature called ECS scheduled tasks. It's basically croned, but for containers. And this is actually, we just started using it recently, but it's really, really nice because every environment tends to have that one crusty batch box. It's like, it's a Solaris machine covered in dust that someone set up 20 years ago, but you can't touch it because it runs all the batch jobs. And then you're like, well, I want to put this other one on. Oh, it's only got PHP 5. I need PHP 7. It's like, no, can't do. That stuff's awful. The cool thing about ECS, you can say, I've got this task with a container in it. Can you please run it on this cron schedule? It will do that. It will launch a task. When the task terminates, it will tear it down. Awesome. No longer having a single point of failure. And of course, it will obey all the standard cluster placement rules and HA stuff and things like that, which is awesome. I use ECS as a dumping ground for my reservations. So if you've got large deployments, you tend to be reserving your instances to get your 40% savings for your beer fund. But of course, what tends to happen is Amazon, for some reason, keep innovating and give you a nice, shinier server that's much, much faster than the last server. And at some point, you decide, you know what, I'm 11 months in, I've made my money back, I'll take the new version to get the performance increase, and you've now got a whole bunch of, say, R3s lying around. Well, what you can do is you can create an additional autoscaling group for the machine types you don't want, fix its size, so it's the exact number of reservations you've got, and then just dump them all into the cluster as additional compute resource or memory resource. It actually works really well. So I did that. We just reserved a whole bunch of new machines. For the last couple of months, I just dumped them all in ECS. I'd already made my savings back, but it allowed me to get a little bit extra value for money out of those machine types, which is quite handy. There's flexible placement strategies. So you can say to ECS, look, I want you to bin pack. I want you to squeeze everything as much as possible into as few servers as possible. Or you can say, you know what, I don't want containers to feel too pressured. Just spread them out across the cluster. Let them hang out. Or things like make sure this container is only ever on one server at a time, which is not really that useful because if you have a container that needs to be on one server at a time, it's probably something like a fixed port, and ECS will already figure out fixed ports as a part of this placement strategy. So if you've got two containers that will only run on port 5000, it's not going to try and run them both on one box. It will figure that out. You can attach network storage in the form of EFS. You can pass volumes through from the underlying host and things like that. Super easy to pick up and build, particularly from late 2017, once all like the CodePipeline stuff came out. Makes deploying this stuff much, much easier. And I'll just as a briefly mention, it does also support Windows. It's not a Linux only thing. So if you're a Windows shop and you're experimenting with Windows containers, ECS actually can support that for you. I haven't used it, so I can't comment on it, but it is actually a thing. Nothing's completely perfect. There's a few annoyances. So CloudFormation is treated as a second-class citizen. So whenever ECS rolls out a new feature, there's often a sort of like a 50-50, will it be in CloudFormation, won't it? And sometimes it takes a while to emerge, which is a bit unfortunate. And the API can have its own deficiencies too. For example, it's possible to set a placement strategy when you create a service, but you can't update a placement strategy after you've made a service, which just seems like a really weird caveat to have, but for whatever reason it's been the case for quite some time. There's no good solution for global services. So it's quite common that you want to run something like a Datadog's a great example, like a performance monitoring tool across all of your servers. And you want exactly one copy everywhere. There's a few hacky ways of doing it with ECS, but there's no equivalent of like a daemon set in Kubernetes where you can say, I want this container on every machine. And it's a real problem for things like Mongo, where you want to run the Mongo router, because things like a Datadog, I could just launch as a background Linux service on the host, or I can launch it as a container from the host itself, from systemd. But things like Mongo are a requirement for the application to work. I don't want my application container starting up until the Mongo container is ready to go. So all these little hacks to be able to run it everywhere fall apart. So the only real solution we've done is that we've bundled in every task, there'll be a container for the app and then a container for Mongo. It's not end of the world, but it just means you've got just a shitload of Mongo containers everywhere. But it's web scale, so it'll be fine. I'm sure nothing could go wrong. The UI could use a little bit of love. It's not too bad. It's getting a lot better lately. But there's just times that you get a little bit annoyed with aspects not working quite as you'd expect. And I guess the other real big issue is just the whole unknown aspect around the future in terms of where does Kubernetes sit versus ECS. ECS has done a really good job of rolling out new features year on year, but Kubernetes has a whole bunch of momentum beyond the Amazon community. So it's kind of like, is that going to overtake it with all the cool stuff or not? Probably the only thing I can say is that at the moment it feels like ECS is going to be a really, really good my first container orchestration technology for anyone who wants relatively simplistic requirements. For example, in our case, we didn't really need stateful systems and containers. We just needed a whole bunch of stateless web applications that all followed 12 factor. It was really, ECS had every feature we needed. We're not missing functionality. Whereas if I wanted, heaps of stateful workloads and daemon sets and things like that, Kubernetes looks like it may be more attractive in that space. And of course, it's Amazon only, but if you're here, you're probably drinking the Kool-Aid and you're not too worried about that. So thank you. That's a whole bunch of information really, really quickly, I know. I've got a whole bunch of other Amazon talks if you're interested in this sort of stuff, so feel free to check that link out and you can